Hey yo everyone, this is your struggling CS student and today I'll be solving the LeetCode weekly premium problem. I just solved the LeetCode daily 2471. I just got cooked by the problem, but hey, fuck it man. Let's try to solve this and yeah, hope we can get a job, improve our lead coding skills. Okay, so today's problem, 1644, lowest common ancestor of a binary tree 2. Okay, I solved LCA before, so let's see what's so different about this problem. Given the root of a binary tree, return the lowest y that is on a path from x to some leaf node. Okay. Yep. 4 is 5. Node 10 does not exist. 10 power 4. Can you find the LCA traversing the tree without checking node's existence? Or what does this even mean? P is not equals to Q. Okay. So lowest common ancestor, very classical problem. Now the variation of this problem is just that P and Q might not exist in the tree. So just gonna draw it out. So there's some tree here, and you're given. So the problem is you're given P and Q, which are some nodes. Yep, just some nodes, and all the values in the tree are unique. And let's say if you find P here and you find Q here, then the lowest common ancestor is P, because they allow a node to be descendant of itself. So yeah, but then if you find P, you find Q, and your lowest common ancestor is just a common parent. It could be something like this as well. Then this is the lowest common ancestor. So it's like this. Okay, so if you solve LCA before, this would not be too hard, I think. But I just got cooked by the last question, so we shall see. Anyway, I did solve LCA just yesterday because I was warming up for an online assessment from a company I wouldn't say its name of. But yeah, so this is still fresh in the memory. Hopefully I can solve this quickly. And okay, let's try to solve the normal version of the problem first. So how do we solve the normal version of the problem? Well, when we look at a tree problem, we always think of tree traversal algorithm. So either pre-order, in-order, or post-order. Here you can see that, hey, given a node, right? Suppose we find P and Q in some way in the subtrees of a current node. So the square one is the current node that we're considering. If we find P or Q, this must mean that this is the LCA. So if you know tree traversal algorithms, then you will know that if we want to process the children first, then we need to do some sort of post-order traversal. So let's try to solve the normal variation of the problem and go from there. So post-order, then we do node. If not node, we return none. And it's post-order node dot left, post-order node dot right. So this is very basic recursive traversal. Post-order node dot. Can we return null? Yes, we can return null. Post-order root. So one of the tricks I use to remember which order to do the traversal is, well, if it's, you always have these two lines of code. If it's pre-order, then you do some sort of processing before you traverse the tree, processing here. If you do in order, then you do the processing here, and then if it's post-order, you do the processing here. So here, because it's post-order, we'll do the processing after we have processed the child or the subtrees first. So suppose this returns us left, and this returns us right. So what does this mean? This means that if node is equals to P or node is equals to Q, that means yeah, which is either P or Q. And we have found either left or right. If left or right, or this must mean that I am the lowest common ancestor. Okay, L if uh, okay. We can say if left or right, then left and right actually. We return the node itself as well. Else, what do we return here? What do we return here? Well, if node is equals to P, or this condition. Return the node itself. We'll return that. Is this good? Not really. 3. Okay. Why do we return 3? Shit, now we're returning the root. Okay, I solved this problem yesterday, but yeah, I'm still getting my ass kicked. Yeah, I remember I solved this problem yesterday, but it was not a very clean solve. If left or right, oh shit, okay. If left or right and this condition, then we return the node. Okay. If left and right, and node is equals to P. If left, maybe? Wait a second. Okay, so if left or right, and we are either P or Q, then return the node itself. Left and right, then return the node itself. Okay, that is correct. Else, that means we are found that if so, at this point, left and right is both false, and if we are either one of P or Q, oh, I see. Okay, okay, I'm dumb. I'm dumb. We have to use the values itself. Yeah. Dot val. Dot val. Dot val. Dot val. Dot val. It's still 3. Oh my days. Wait, what's
no! Oh no!
what the hell? Why is it always 3? What the? This returns the node itself. Uh, uh, okay, this example 6. Okay, we didn't find anything. 7. Didn't find anything. 4. We didn't find anything but 2 here. We found this guy. 5. Oh, days. What the hell? Okay. If left, then left. If right, then right. This is for... Oof, really? It's a bit sus. Okay. 5. Put on down, put on down, put on down. Return left. Okay, at this point, so from the right side, okay, that means this node has to be returned, right? So on 3, my output is 3. If left, and node dot down, why is 3 written here? If left, else. If Oh my days. Wait, really? Okay. Okay, now we have to solve for the null case. I returned 5. Return 5. Oh, okay. Means I see, okay. So, okay, so that's where the problem differs. I don't think it's too challenging, but maybe that's why they put the follow-up question without checking the node's existence. Okay, so basically here we found P, but and we didn't find Q, but the result is as if we found both P and Q. If you see the case from um, case 2, right? So what we can do is found, maybe we can do it at the end. Found P is equals to false. Found Q is equals to false. Oh shit. If the node's value I guess we can just do which is a bit sketch. Found is equals to 0. Rest equals to this. Then rest if found is equals to 2, else none.
Hooray!
It passes the sample test case, but I'm not super confident that this will work. And it's not the best code I've written, but you get the idea. Like, I'm really curious about this thing though. Okay, what's the time and space complexity here? Yeah, the time and space complexity is just O of n, where n is the number of nodes in the tree. You could have a worst case scenario where the tree is just a linked list from the root to the leaf, and well, there you go. You have to traverse obviously all of the nodes, and then because we're using recursion, you take up to n functions stacks. So space and time complexity is ON. Is this correct? I'm not super confident. I'm gonna YOLO submit. I mean, in an interview situation, yeah, this is not the cleanest code. OA setting, as long as you pass all the test cases, plus the hidden test cases, you are good. So I'm just gonna YOLO submit, see if it works first. Okay, accepted, good. I'm glad that this didn't take too long. Well, let me see. Can you find the LCA traversing the tree without checking node's existence? What does that even mean? Without checking node's existence. What? Don't you kind of have to check no matter what? This is okay. Well, let's see. What's the time and space complexity? Linear, linear. Okay, good. Right. This is a follow-up. Da, 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 da. Okay, let's see some of the examples here. Yeah, if you find P and Q, and when you return the links, then this is just the LCA. So if you compare it against our code, this is the case where it's this case. So just return the node itself. Here is so P is the LCA, that would be this. Likewise, this case is also this case. Yeah, this is no common ancestor. No common ancestor. Yep. Modify LCA. Okay, let's see how they do it. Okay, yeah, good one, bro. Oh, okay. Okay, very clean code. Good job. Yay. Unlike mine, but whatever. Yeah. Okay, let's just read the code. Found the target. Yeah. Okay. If the node is none, return none. Or we find P, we find Q. Huh. This is the idea that I had. Yeah, it seems like most people also had the same idea. So yeah, we just maintain two Boolean variables. That's what I initially thought of. But then again, because of the way I set up my conditional structures, just using a counter variable was more convenient. Let's see this one. Okay. Okay. Yeah, why is this so complicated? This part. Lowest common ancestor. LCA of PQ first. Verify if Q is in sub-3. Ah, okay, I see. I see, okay. So, okay, I see. So what LeetCode's first approach is saying is we will just reuse the code from the just reuse the code we used to solve LCA where both of P and Q values exist in the tree. Okay. Now, if they exist in the tree, then with the previous example, you will see that uh, basically the lowest common ancestor will be returned. So if let's say P is here, and Q is here, then we just return P. That's if both P and Q values exist. But suppose Q does not exist, then in our original solution, P is returned. So we need to check against the edge case. And how I check is to use a counter variable, but how they are doing it is first they return the LCA first, right? So it could be P, it could be Q here, it doesn't really matter. But then what they do is then use depth first search to find the other node in the subtree itself. So if let's say we have P here and you have Q here, then I mean it's just the same. P is returned in the original answer here. Then here is just checking if Q is in this subtree, right? Verify Q is in subtree of P. This is just the opposite. And else you just return the answer. So it could be the case that P is here and Q is here, and this node is returned, which is fine in this case. Well, this is the LCA, but this just handles the case where one of the values, it handles this case, right? This can be interchanged, where P is returned, but then Q might not exist, right? Q might not exist. And so this is what these checks are for, is for. Okay, sure. Yeah, okay. Anyway, solve is a solve, so I'll take that. Hope you enjoyed this video. Hope you have a great day ahead. Goodbye.